And 2-1 is patterns and inductive reasoning. Patterns and inductive reasoning. Does anyone have any idea what inductive reasoning is? You're backing up something? Inductive reasoning. It's critical thinking. Okay, here it is. Inductive reasoning is reasoning based on patterns that you see. So it's thinking logically about like, well, what makes sense? What should come next? If we're looking at the scenario, what do you expect to see next? Okay, so that's where patterns come into play, because a pattern, you know what you're expecting to see next. So for instance, if I gave you this setup, okay, I want to know what is the pattern that you're seeing, and therefore what are the next two terms that you would get, Jordan?
Multiplying by 3.
Right, you are multiplying by 3 to get to the next one each time. So times 3, times 3, times 3, right? So your pattern, they're going to ask you for the pattern, which you would just say times 3, and then the next two terms. What would your next two terms be? 243. 81 times 3 is 243. And then 729. Multiplying that 243 times 3. Okay, so looking for patterns. That's inductive reasoning. But it's not always going to be with numbers. So what if I gave you this one? Let me get this out of here first. Okay, so if we did, bear with me on my drawings here. They're not going to be perfect, but you'll get the idea. All right, let's say I have this picture, and then I have this picture, and then I have this picture. Okay? Now, here's where you have to be a little bit creative with how you describe this, because it can't be, you have to be specific, right? What is happening to get from the first to the second to the third? What are you doing? Okay, but adding a line, so my next one could be 1, 2, 3, 4, 5, 6. Like I'm just adding a line somewhere. The shape inside is gaining one side, right? That'd be a good way to say it. Or we could say a polygon with one more side than the one before it, right? So be specific when you name your pattern. So I would say my pattern is something like you add a side to the polygon inside the circle. Okay, something along those lines. So then if you had to draw your next two terms would be a hexagon and a what? Heptagon. Good job. So 1, 2, 3, 4, 5, 6. Sorry, not beautiful, I know. And then 7. 1, 2, 3, 4, 5, 6, 7. Try to make them the same size. Mine are not. Sorry. Nope, hexagon is 6, heptagon has 7. So you're adding one side each time. Octagon is 8.
Heptagon existed.
Yes, well, now you do. We'll talk about it more later in this school year. Okay, so that is patterns, right? And you're going to do a lot with patterns. There's some, I'll be real impressed. There's some in the homework that take a little extra thought. I will be really impressed if you can figure out all the ones in the homework, because there's a couple in there that I love them, but a lot of times people have trouble figuring out what they are. It's not colors. It's with letters. It's letters. Okay, what's a conjecture? If you make a conjecture about something, what is that?
A statement.
A statement, a thought, a hypothesis, kind of a guess in a way. A conjecture is a conclusion that you're going to reach using something like this, using inductive reasoning, right? So your conjecture is basically, I think the next two terms are going to be this and that, right? You're making an assumption. You're making a rule, in a way, for what is to come. So you're going to be making some conjectures. Here's your first one. Let's say we have these circles. Okay, so if I have those three circles and I said, what conjecture could you make about the number of regions um, 20 diameters would form? What's a diameter? A line across the middle, okay? So right now we have one diameter here. So if this is one diameter, how many separate regions did it make in that circle? 2 regions. Okay, how many diameters in the second one? 2 diameters in the second one, which made how many regions? 4 regions. Okay, the third one, how many diameters do we have? 3 diameters. Oops, and that made how many regions? 6 regions. Okay, so we're looking for a conjecture as to what you think the number of regions would be for 20 diameters. Excuse me, Aaron.
So if I know how many diameters there are, it's the amount of lines, right?
The number of lines that go all the way through. Yep, so this is a diameter. These are diameters. These are diameters, right? All the lines that cut through. Okay, so if 1 diameter got you 2, 2 got you 4, and 3 got you 6, then 20 diameters would get you 40 regions. Basically what you're saying is the number is doubling each time, right? 1 became 2, 2 became 4, 3 became 6. So we would expect that if you drew in 20 diameters, we would get 40 regions. Okay, so you're just trying to make a conclusion. You can try to draw that. I would not draw it well, so I'm not even going to try. But yes, you could try to draw that. Okay, one rule about making a conjecture is you need to gather enough information. So like if I just said 1 and 2 and I stopped at that first picture, that's not enough information. You need to test it a few different times to make sure that we're getting to where we want to get. So we're going to do another conjecture. Example 3 here. We're going to make a little chart to test out our conjecture here. So let's say we're going to deal with the sum of even numbers. Okay? So if I said this is going to be the number of terms, and this is going to be the sum for those terms. We'll see if we run out of room here. Okay, so if I have one even number, what's the first even number? 2, right? So the sum of the first one even number is 2. If I had the first 2 even numbers, that would be what? 2 and 4, right? 2 plus 4 gives us a sum of 6, okay? If I had the first 3 even numbers, what would your sum be? 2 plus 4 plus 6, so you would get 12, okay? If I had 4 even numbers, 2 plus 4 plus 6 plus 8, I would get 20, okay? So here's what I want to know. What would the sum of the first 30 even numbers be? Okay. Now here's the deal. Do you really want to go 2 plus 4 plus 6 plus 8 plus 10 and all the way up to 30 terms? No. So we make a conjecture. We figure out what is the pattern that we're seeing, and then we plug in 30 to figure out what 30 would be. Okay? Now, this one takes a little bit of thought. What is it?
930.
930 would be your number? How did you figure it out?
30 times 31.
Right. How'd you get there?
By listening.
By looking at your numbers, right? By looking at the information we have here and figuring out what is the relationship, okay? So here's the deal. For this first one, well, 2 is a little harder to see it with because you're not comparing so much. But when you compare these, right? 6 is like saying 2 terms times the number of terms more than that, right? 2 times 3. 3 is like saying 3 terms times the number of terms more than that, 4 terms. 4 is like saying 4 times 5, right? That gets you 20, that gets you 12, that gets you 6. So if you're always taking the number of terms times 1 more than that, so 30 times 31 for the first 30 terms. So you would do 30 times 31, and you get, what did we say, 930. Okay, so you have to look for a pattern, and they're not always just the easiest thing in the world to find. You have to think about, how does this number relate to that number? How does this number relate to that one? How does 20 relate to 4? Okay, so what is the relationship happening there? Questions on that? Yeah, Aaron.
Backtrack like so far. So how did you get 12 again?
12 was the sum of the first 3 even numbers. So 2 plus 4 plus 6 gets you 12, right?
How'd you get 6 then?
That's the sum of the first 2. So this is how many terms. These numbers here, that's how many terms do you have. So I have 2 even numbers, or I have 3 even numbers, or I have 4 even numbers, right? So 1, 2 even numbers got me 6. 3 even numbers, 1, 2, 3, got me 12. 4 even numbers, 1, 2, 3, 4, got me 20, right? So then once you have those sums, then you look at the relationship. How did I get from 2 to 3? How did I get from 3 to 12? How did I get from 4 to 20? Well, this one I multiplied by 3. This one I multiplied by 4. This one I multiplied by 5. So you're always multiplying by 1 more than the number itself to get there, okay? Okay, last thing. Not all conjectures that you make will be true, right? It might look like you see a pattern, but if you kept going, it doesn't always work out that way. So that's when we find what are called counterexamples. We talked a little bit about those yesterday. And we're going to talk a little bit about them again today. So this is example 5. And I want you to find me a counterexample. So you're looking for something that your hypothesis is true, but the conclusion would be false. Okay? So hypothesis true, conclusion false. So for this first one, if I said, if the name of a month starts with J, it's a summer month. Okay, so here's how counterexamples work. You have to have the first part true. So we have to have a month that starts with J, but the second part false, the conclusion false. It can't be a summer month. So what is your counterexample? January. Okay. How about this one? You can connect any 3 points to form a triangle. Okay, so that's our statement. So basically it's saying if you can connect any 3 points, then you can form a triangle. So we want to connect 3 points, but it not make a triangle. What's that going to look like? What's your counterexample?
Two sides are both 2 inches and one side is 5 inches. So that would make a triangle. So
Okay, but not segments. Any 3 points.
a line.
Connect any 3 points. A straight line, right? If you put them a point here, a point here, and a point here, those are all connected right now, right? And they are not making a triangle. So this picture would be your counterexample. Okay, 3 points that are all connected but not making a triangle. You with me, gentlemen? Okay, last one. If I said, when you multiply a number by 2, the product is greater than the original. Okay, when you multiply a number by 2, the product is greater than the original. So we're looking for multiplying some number by 2, but not getting a bigger product for the new one. 0. Okay, so if you do, ow. So your counterexample is 0 times 2 gets you 0, right? That 0 is not bigger than what you started with, 0. Okay, what's another option? A negative, right? -2 times 2 is actually a smaller number, -4. So -2 is actually bigger than -4. Okay, so you're just looking for, how could I prove this false? Is your counterexample. Okay? Questions on that? All right.